node. If there is a path between node, that is called as an edge. That is the key concept used here, nodes and edges. The nodes are sometimes also referred to as vertices, and the edges are lines or arcs that connected and two nodes in the graph. So the nodes are sometimes referred to as vertices. A node or otherwise called it as vertices. Vertices and nodes both are same. Edges are, there is a path between vertices or nodes, that is called as an edge. That is the basic definition for nodes and edges. A graph consists of a finite set of vertices and set of edges which connect a pair of nodes. If there is a path between pair of nodes, that is called as an edge. That is the definition for edge and also node. Here is the diagram and also the introduction about the graph. A graph is a pictorial representation of a set of objects where some pairs of objects are connected by links. There is a link between A and B, B and E, D and E, B and D, A and D, A and C, C and D. These are all links. The links are called as an edge. If there is a path between B to E, that is called as an edge. If there is a path between A to B, if there is an edge. And also A, C, B, D, E. These all are called as vertices. Vertices are nodes. The circle, data inside the circle, that is called as a vertices or node. A node or vertices is called as the data within a circle. It is called as a vertices. If there is a path between two vertices, that is called as an edge. Here, how many edges are there? A to B, A to C, A to D, C to D, B to D, B to E, D to E. These are all edges. Totally 1, 2, 3, 4, 5, 6, 7. 7 edges are there. Totally 7 edges are there. 5 nodes are there. See the graph within in this graph there are 5 nodes and 7 edges are there. Here is also a example for graph. A graph is a pair of, it is also the definition for graph. It consists of vertices and edges. V is denoting vertices, E is denoting the edges. Sets with vertices and edges, where V is the set of vertices and E is the set of edges connecting the pairs of vertices. A, B, C, D, E are all vertices. There is a path between A to B, A to C, C to D, B to D and D to E. These are all called edges. These are all called edges. These are all called vertices or nodes. In this given graph, vertices are A, B, C, D, E. Edges are A, B, A to C, B to D, C to D and D to E. These are all edges within this graph. In this graph, AB, AC, BD, CD and DE. These are all edges. Here is the other diagram for you. Here, how many nodes are there is 1, 2, 3, 4, 5, 6, 7. 7 nodes are there. And then how many edges are there? 1, 2, 3, 4, 5, 6 edges are there. Level wise, we can classify these nodes. It's a 0th level. It's first level, it's second level, it's third level. Like a tree diagram, it is also classified as level basis. It's a 0th level. The starting node is called as 0th level. It's first level, it's second level, it's third level. The graph is also denoted as level wise, like trees. Vertex, each node of the graph is represented as a vertex. In the following example, the labeled circle represents vertices. Following example, given example, this is called as vertices. I already told you. And then thus A to G are vertices. We can represent them using an array as on the following image. So we can represent the graph using array or using adjacent list. We can represent the graph using an array or adjacent list. Here A can be identified by index 0, B can be identified by index 1. In the previous diagram I told you, A can be identified using the index 0 and B can be identified using the index 1. This is also identified by using the index 2. This is 3, this is 4 and 5, 6. So using the index position, we can specify the particular node. So for that, here A can be identified by using the index 0, B can be identified using the index 1. So like that, we can specify the index position for each data. Using array representation, we can specify the index position for each data. The procedure is A, B, C, D, E, F, G are the data. First, it is denoted as index position 0. It is denoted as index position 1. It is denoted in the index position 2. It is denoted in the index position 3, 4, 5 and 6. We can represent the data using the index position 0 that indicates A, 1 that indicates B, 2 that indicates C, 4 that indicates E. Likewise, we can represent this graph structure using an array. Edge represents a path between two vertices or a line between two vertices. In the given example graph, the lines from A to B, B to C, and so on represent the edges. We have already discussed about this. Next one, adjacency and path. What is an adjacency and what is a path? Adjacency is two node or vertices are adjacent if they are connected to each other through an edge. If it is an edge, that is called as an adjacency. In the graph, B is adjacent to A. B is adjacent to A. There is a path between A to B. B is adjacent to A. B is adjacent to A. C is adjacent to B. C is adjacent to B. C is adjacent to B. There is a path between B and C. So C is adjacent to B. Next, likewise, we can represent all the nodes. Here, E is adjacent to A, F is adjacent to A, and also G is adjacent to F, D is adjacent to C. If there is a path between two vertices, that is called as adjacency. A for the node A, based on the node A, B has adjacency, E has adjacency, F has adjacency, and also C has B, G has F, D has C. These are all the adjacency for the given graph. These are all the basic terminology. Next, what is a path? Path represents a sequence of edges between the two vertices. In the following example, A, B, C, D represents a path from A to D. I would like to traverse from the node A to D. You already studied about what is traversing. Traversing is we have to visit all the vertices at least once. We have to visit all the data at least once. Here, I would like to traverse the node D. I would like to traverse the node D. What is the possibility I want to visit the node from A to D? First, we have to traverse to A. My target node is D. If there is a path to D, there is a path using the nodes B and C only. We cannot use E, F, Z. There is no path using these vertices. E, F, Z are not a possible nodes to traverse the node from A to D. So only possibility is A to B, B to C, C to D. We can traverse the source node A to D using the path A to B, B to C, and C to D. This is the only possibility we can traverse from A to D. A, B, C, D represents a path from A to D. That is a path from A to D. That is called as a path. The path represents there is a possibility to visit the source vertices to destination vertices. That is called as a path. Here is a diagram, for example. It is a graph. It is a graph. It is a tree. So you already studied about trees in the previous classes. It's a tree. It's a graph. That graph is not be a tree. It is a graph. The graph cannot be a tree, but a tree can be a graph. You understand the basic concept? A graph cannot be a tree because of there is an edge between D to E. If there is a path to D to E, it is a closed circle. There is no possibility in trees as a closed circle. We cannot use closed circle in trees. It is a graph. The graph cannot be a tree, but it is a tree. A tree consists of the data A, B, C, D, and E. These are all the nodes used in the graph. There is a path between A to B, A to C, C to D, C to E. It's a tree. The tree is also act as a graph. A tree is also act as a graph, but a graph cannot be a tree. That is a basic concept. You have to remember this. In the objective type question or gate question, the questions may ask whether the graph is treated as a tree or a tree is treated as a graph. The questions may ask in the examination also. So you have to know this basic terminology. A tree can be act as a graph, but a graph cannot be act as a tree. So using adjacency matrix, there are second way we represents the adjacency matrix. Second way that is used to represent the graph is adjacency matrix. Here is the diagram. A, B, C, D and E are the vertices. A to B, A to C, A to D, B to E, D to E, D to D is also a path. It represents the cycle. D to D. The node visits the node again. D to D. A to B, A to C, A to D, B to D, B to E, C to D and D to D. There is a path. It is a given graph. We have to represent this graph into adjacency matrix. What is an adjacency matrix? We have to represent what are all the nodes here. A, B, C, D, E are the nodes. And then A, B, C, D, E are the nodes. If there is a path from A to A, it represents 1. If there is a path from A to A to B, A to C, A to D, A to E, and then B to A, B to B, B to C, B to D, B to E. If there is a path from one vertices to another vertices, then we have to put 1. Otherwise, we have to put 0. It contains the binary values only, either 0 or 1. If there is a path, it represents 1. If there is no path, it represents 0. If there is a path between A to A, there is a path between A to A. There is no path from A to A. There is no path from A to A, like this. There is no path from A to A itself. There is no path. So we put 0 here. And then move on to the next node. If there is a path from A to B, there is a path from A to B. There is a path. So we have to put 1. And then if there is a path from A to C, A and C, there is a path, there is an edge there. So we have to put 1. And then if there is a path from A to D, there is a path, we have to put 1. And then check A to E. If there is a path from A to E, there is no path, straight path from A to E. So we have to put 0. There is no straight path from A to E, put 0. It is the first, it's for first row. We are comparing with the node A, we have to put 1s and 0s. If there is an edge between two vertices, then we have to put 1. Otherwise, we have to put 0. It is considered as direct edge. If there is a edge that is called a direct edge, then we can put 1. So next one, B to A. If there is a path from B to A, we can traverse from B to A also. Put 1. B to B, there is no possibility to visit the node B to B. There is no cycle here. So we cannot traverse B to B, put 0. And then B to C. B to C, there is no path from B to C, put 0. B to D, there is a path from B to D, put 1. B to E, there is a path from B to E, put 1. And then next move on to the next node. From the node C, here is the node. From the node C, C to A, there is a path from C to A, put 1. And then C to B, there is no direct path from C to B, put 0. And then move on to next node, C to C, there is no path from C to C, put 0. Next, C to D, there is a path, C to D, put 1. And then C to E, there is no direct path from C to E, put 0. When next node D, from this node, D to A, put 1. D to B, put 1. D to C, put 1. D to D, there is a path from D to D also, so put 1. D to E, put 1. So all are ones. Comparing with the node D, all are nodes. So all the nodes having the edge from D to all the other vertices. Then next move on to the next node E. E to A, there is no path. E to B, there is a path. E to C, there is no straight path. E to D, there is a path. E to E, there is no path. So 0, 1, 0, 1, 0 is the adjacency matrix for the given graph. So adjacency matrix is the important aspect. It is also called in the examinations. Adjacency matrix is we have to represent the data in binary format. If there is an edge between two vertices, then we have to put 1, otherwise put 0. The edge should be a direct edge. That should not be a combination of edges. So if there is a, for example, A to E, there is a possibility to traverse from A to E. How can we visit A to B, then B to E? Then only we can visit A to E. But we cannot consider for the adjacency matrix A to E, there is no straight path. So put 0. A to E, put 0. It is called as adjacency matrix. Using adjacency matrix, we can identify there is an edge between two vertices. Next one, directed graph. Directed graph is otherwise represented as digraph. Directed graph is otherwise represented as digraph. Digraph, otherwise directed graph, both are same. A directed graph or digraph is a set of vertices and a collection of direct edges that each connects an ordered pair of vertices. That is 1 to 3. There is an edge. It is a directed edge. 1 to 3. There is only one possibility. We can traverse from 1 to 3 only. We cannot traverse 3 to 1. But in this graph, we can traverse either direction, A to B, B to A also. But in this diagram, we can traverse only from 1 to 3. We cannot traverse from 3 to 1. That is the difference between directed graph and undirected graph. It is an undirected graph. It is a directed graph. Directed graph contains an arrow. That arrow indicates where we have to visit. Where we have to visit. In this diagram, we can visit from 1 to 3, 1 to 2, 1 to 4. From 3, we can traverse only to 6. From 4, we can traverse only to 3 and 7. From 2, we can traverse 4 and 5. From 5, we can traverse 1, 4 and 7. From 7, we can traverse only to 6. From 6, there is no possibility we cannot traverse from 6 to any other vertices. So using directed graph, we can easily identify which one is the source, which one is the destination. But in the undirected graph, we cannot specify which one is the source, which one is the destination. From the node A can be act as a source node and also a destination node. Starting from E, we can traverse E to D, D to C, C to A. We can traverse C to B, B to A. So either direction we can traverse. Using undirected graph, we can easily traverse in either direction. Both the directions we can traverse. But in the directed graph, we can traverse in only one direction, that is in the directed arrow. The arrow represents where we have to visit. 1 to 3, 1 to 2, 1 to 4. So the arrow indicates where we have to visit the data. That's the difference between directed graph and undirected graph. So directed graph is applied in flowcharts. You already studied about flowcharts in previous semester examinations and also previous subjects in the like Python programming, C programming. We have in any other programming language you have studied about flowcharts. Using flowcharts, we can specify the directed graph. Within that graph, we can specify the flow of execution. The statements flow of execution. Using the directed graph, we can specify that. So directed graph is applied in flowcharts. Next one is undirected graph. So I already told you, no arrow mark is specified in undirected graph. We can traverse in any other direction, any direction. We can choose anyone as source node and anyone as destination node. From 6, we can traverse to 1. From 1, we can traverse to 6. From 1, we can traverse to 7. From 7, we traverse to 1. Either direction we can traverse. 1 to 2, 2 to 3, 3 to 5, 5 to 6, 6 to 5, 5 to 3, 3 to 2, and 2 to 1. Say another way, 1 to 4, 4 to 3, 3 to 5, 5 to 7, 7 to 5, 5 to 3, 3 to 4, and 4 to 1. Either direction we can traverse. In undirected graph, using undirected graph, we can traverse in both directions. In both directions, like forward direction or backward direction. Where the undirected graph is applied, airline route map. In route map, there is no directions are given. In Google Map, there is a direction. The direction will guide us to traverse from source stations to destination station. But airline route map, there is no direction. So based on the map, the pilot will guide the flight to required position. So example, airline route map, undirected graph is applied in this airline route map. Direct graph is applied in flowchart. So these are the two real-time examples using graph. Another basic concept is subgraph. A graph whose vertices and edges are subsets of another graph. For example, 0, 1, 2, 3. These are the four. These four are the vertices in the graph. But 0 is a subgraph. 0 alone is a subgraph. 0, 1 is alone a subgraph. 0, 1 is also a subgraph. 0, 1, 2, it is also a subgraph. 3, 1, 2, it is also a subgraph. 0, 2, 1, 3, it is also a subgraph. A subgraph, a graph whose vertices and edges are subsets of another graph. A graph, it contains 4 nodes, 0, 1, 2, 3. We can split this graph into tree structure, 0, 0, 1, 2, 3, 1, 2, like this. It is a tree, it is a tree, it is a tree, it is not a tree, it is not a tree, it's a tree, it's a tree, it's a tree. So the nodes are split into subgraphs. Subgraphs is nothing but the vertices and edges are subsets of another graph. 0, 1, 2, 0, 0, 1 and 2. These are all the subgraphs of this given graph. It's a given graph. These are all the subgraphs of the given graph. This is called as subgraph. A complete graph. What is called as a complete graph? If there is a path from any source node to any destination node. If I would like to traverse from A to D, I can traverse A to D. It is possible. If I want to traverse from A to C, there is a straight path. I can traverse. A to B, possible. A to E, it is also possible. From the node B, we can traverse in all the. We can traverse to all the vertices. B to C, B to D, B to E, B to A, and then from C, C to B, C to A, C to E, C to D. From the node D, D to C, D to B, D to A, D to E. From the node E, E to A, E to B, E to C, E to D. A complete graph. When we say a graph is a complete graph, is that graph should not be a directed graph. The graph should not be a directed graph. That the graph should be a undirected graph. Then only the graph can be a complete graph. A complete graph is a simple undirected graph in which every pair of distinct vertices is connected by a unique edge. Every node contains unique edge to any other node. C contains the unique edge to P. It contains the unique edge to A. It contains the unique edge to E. It contains the unique edge to D. A complete digraph is a directed graph in which every pair of distinct vertices is connected by a pair of unique edges. Every edge is called as a unique edge. It is called as a complete graph. You have to remember both the 2 key points here. When we say the graph is a complete graph, the graph must be an undirected graph, and also there is a unique path from a node to another node. A unique path from one node to another node. That is called as a complete graph. These are the 2 key aspects we have to remember. Next point, out degree and in degree. In degree and out degree. How we calculate out degree and in degree using graph. The graph should be a directed graph. The graph should be a directed graph. Then only we can calculate the out degree and in degree of a graph. For a directed graph and a vertex, the out degree of refers to the number of arcs incident from. Number of arcs, that is called as an arrow. Number of arrow that represents. So it is called as, so B, from the node B, how many in degrees are there is 1, 2. These 2 edges are towards B. Towards B. So in degree of B is 2. What is the out degree? From the node B, how many possible paths are there? That is called as out degree. From the node B, only one out source is there. Out arrow is there. It is out degree. Out degree is 1. In degree is 2. From the node B. From the node A, how many in degrees are there? 0 in degree. How many out degrees are there? 2 out degrees. From the node A, 2 outgoing arrows are there. So 1 and 2. 2 out degree, 0 in degree. For the node F, how many in degrees are there? 2 in degrees are there. Out degrees are 0. From the node D, in degree is 1. Out degree is 1. For the node G, out degree is 1, 2, in degree is 1. From the node C, in degree is 2, out degree is 1. So this is called as in degree and out degree. I repeat once again. So in degree is calculated how many incoming arrows are towards the node, particular node, and then out degree is calculated how many outgoing arrows are from the node. here 1 outgoing arrow, 2 incoming arrow. It contains 2 in degree and 1 out degree. Based on the arrow mark, we can calculate the in degree and out degree of the each vertices. That is called as in degree and out degree. You must remember all the things. So for complete graph, it must be a undirected graph, and each node consists of edge from other nodes. Each node consists of edges from other nodes. That is the complete graph definition. For calculating the out degree and in degree, it must be a direct graph. Based on the arrow marks, arrow positions, we can calculate the how many in degrees and how many out degrees are there. Next, strongly connected graph. A directed graph is strongly connected if there is a path between all pairs of vertices. If there is a path from between all pairs of vertices, 1 to 0, 0 to 3, 3 to 4, and from the node 2 to 1, 1 to 0, 0 to 3, 3 to 4. From the node 0, 0 to 3, 3 to 4, 0 to 2, 2 to 1. So we can traverse all the vertices from any other node. If I want to visit the node from 1 to 4, there is a possibility from 1 to 4, 1 to 0, 0 to 3, 3 to 4. There is a path. If I would like to traverse from 2 to 4, it is a destination node. Anyone we can treat it as a source node. 2 to 4, 2 to 1, 1 to 0, 0 to 3, 3 to 4. It is a destination because of there is no out degree from this node. It is the destination node. So we have to traverse to this towards this node. So from the node 0, we can traverse to 4, 0 to 3, 3 to 4. But another path is also there. 0 to 2, 2 to 1, 1 to 0, again 0 to 3, 3 to 4. Here is also a possibility. From the node 3, we can traverse to 4. So for the destination node, that should be a path. There should be a path from any other node to the destination node. That is called as strongly connected component. And that is called as SCC.
Okay. Sir.
Hello?
Sir, one doubt, sir. Sir, from 4 to 0, how come we can go, sir?
4 to?